Hello, my name is Ivan Nathan Parmenas, and today I will introduce to you about appearance and shape from water reflection. Water reflection has long been a source of artistic inspiration in paintings, architectural design, and modern photography that compose reflection by a water surface together with direct sight of a scene. Water reflection will also give a different vantage point of the scene from the camera viewpoint when captured in a single image, collectively forming a flipped stereo pair. This suggests an opportunity for a single image scene geometry recovery by applying standard stereo reconstruction to estimate scene depth through self-calibrating high dynamic range catadioptric imaging system. However, there are few challenges. The first challenge lies in the fact that water-reflected scene radiance is compounded with environmental light scattered in the water medium and also reflected by the bottom surface. As a solution, we derive a canonical iterative method to recover scene geometry from the direct and water-reflected observations and show that high dynamic range scene radiance can be estimated in the process. The second challenge is the water surface in the image is not always calm and can have waves that leads to noticeable displacements in the reflected observations. As a solution for this, it can be modeled as surface normal variations of the water surface and derive an iterative approach to simultaneously recover the shape of both the scene structure and the water surface. Next, we can categorize water reflection into two types, planar and wavy water reflection. Here in figure 1, we have a planar water reflection that depicts a 3D scene point PW where it is observed twice in the image, the direct observation LCU and the reflected observation LCU derivative. Note that both observations of scene points are captured in a single image and represented by their positions on the image plane U and U derivative. For a calm water surface or a wavy water surface, we estimate the surface normal of the water surface NW from a small set of corresponding pairs of direct and reflected observations U derivative that satisfies the formula below, where A is the intrinsic parameter matrix of the camera and NWX is the skew symmetric matrix of NW. This NWX is a linear constraint on the normal NW, and we can estimate NW from two or more corresponding pairs. While intrinsic camera parameters A can be initialized with EXIF or exchangeable image file format information when available, or with reasonable values common in outdoor photography, which are then refined by the radiometric recovery process. We obtain these correspondences semi-automatically, where we first segment the image into direct and reflected observation regions, which can often be done by just specifying the line where the direct and reflected observations meet in the image, then run generic feature detection and matching methods in these two regions. For a calm water surface, it can also be modeled as a planar reflector. Once we estimate its normal, the direct and reflected observations in the image form a stereo image pair. While for a wavy water surface, the stereo correspondence pairs are locally perturbed by the varying surface normal at each water surface point. In either case, if the displacements due to waves are undone and correspondences are established, we may recover the 3D coordinates of scene points via regular stereo reconstruction from the direct reflected observation point pairs as shown below. This stereo reconstruction requires the intrinsic and extrinsic parameters of the camera. For reflected scene radiance by water surface IR, it can be described by the Fresnel power reflectance F. with the formula below. And figure 2 below also shows the Fresnel reflection on the water surface in effect provides scene radiance captured with spatially varying exposures that are different from the camera. By combining these two radiance exposures, we construct high dynamic range appearance of the scene on the right, which reveals scene details in saturated regions in the original direct view on the left. Assuming that the environmental illumination is uniform across the water surface, a part of this environmental light is transmitted into water, scattered in the medium, and then transmitted back into the viewpoint. Looking back at Figure 1, the scattered illumination is the sum of scattered light from all points along the transmitted path observed at U derivative. On the other hand, the bottom of the water medium at which the light path intersects will have a comparatively weaker radiance, which suggests that we can limit the contribution of water-scattered environmental illumination to that from near the water surface. But when the medium is shallow, the bottom surface reflection will be comparatively strong and instead be transmitted into the viewing direction almost without any scattering. So to recover the scene radiance from the reflected observations, we first estimate the sum diffuse bottom surface reflectance Lg0 and subsurface scattering Ls0 from each of n pairs of direct and reflected image coordinates using the formula below. We can then sift out the scene radiance from the reflected observations of each U derivative by subtracting these additive components and by undoing the Fresnel reflection formula. The recovered scene radiance in the reflected observation is then used for stereo matching with its direct observation. On the other hand, wavy water surface has noticeable waves. We simultaneously estimate the geometry of the waves and the scene. As we can safely assume that the wave amplitude is sufficiently small compared to the height of the camera, we can model them as surface normal perturbations to the otherwise flat water surface. This surface normal variation causes changes in projected image coordinates and their radiance. Using notions depicted in Figure 3, we model this by expressing the reflected observation for a corresponding pair of direct and reflected observations using the local normal of the water surface point. Since our goal is to remove the effects of water surface deformation and associated radiometric change in reflected observation, like image intensity change, by comparing direct and reflected observations independent of the disparity, the main challenge for this is that the angular dependency of the reflected observations only results in a subtle change in image intensity, which is not large enough to robustly separate the water surface normal variation and disparity. So, to simultaneously estimate the wavy water surface and the scene geometry, we formulate it as a 2D image alignment and employ prior knowledge about the scene structure and the wavy water surface. By projecting and comparing direct and reflected observations independent of the disparity to a common image plane, we can achieve 2D image alignment between observations, removing the effects of water surface deformation and associated radiometric change in reflected observation. When waves are erroneously recovered, the recovered scene geometry will subsume the errors in water surface geometry, resulting in a wavy 3D scene structure. Since a real-world surface geometry is in general not wave-like, we can impose a geometric prior on the scene. We employ a piecewise planar geometry prior that encourages the recovered scene geometry to consist of locally planar surfaces. In particular, we segment the direct observation of the scene into superpixels and impose this piecewise planarity on each superpixel. We impose this prior in a coarse to fine fashion, in which the superpixel size is iteratively refined. This, in effect, allows smoothly curved scene geometry while nudging the wave pattern to be explained by the water surface instead of the scene structure. Here are a few results of the experiment using the two methods with controlled experiments and with arbitrary images taken in the wild. Figure 4 below shows a quantitative evaluation using structured light stereo to acquire ground truth depth. From A, a single image with bottom surface reflection and waves, we recover B, an HDR appearance, and CD, dense 3D geometry shown in two views, which agree well with ground truth as E, the percentile error map WRT since depth range. The method also recovers the wave structure as surface normal variations as shown with F, 10 times amplified normal maps. Here, we set up a dual camera imaging system, one to capture the input image for the method, the second camera to reconstruct ground truth depth with structured light stereo reconstruction. This provides per pixel ground truth depth at the main camera. In addition, we create waves by perturbing the water surface to evaluate the method's robustness to reasonably large waves. Next, we also quantitatively demonstrate the effect of self-calibration in Figure 5. The results clearly show that the focal length estimation undoes the skew and results in more visibly accurate geometry. And in Figure 6, it also shows the results of reconstructing the Golden Temple with and without estimation of the waves on the pond reflecting it. The results clearly show that by explicitly modeling the waves as 2D deformations of the proxy plane and imposing natural priors on their shape, they can be disentangled from the target geometry. We also apply the methods to various images either taken by our phone cameras or found on the internet. And Figure 7 shows the single input images and recovered 3D models with high dynamic range appearance. The results shows that the 3D scene structure can be recovered despite waves and complex water surface reflection. It is also interesting to see how the method applies to a wide range of scene scales, ranging from a small bird to a large architecture. Images taken with long focal length tend to result in flatter surface with limited depth variation. The results also includes various types of water reflection, ranging from a puddle to a lake, demonstrating its successful application. So, in conclusion, we have introduced appearance and shape from water reflection to recover 3D geometry and high dynamic range appearance of a scene from an image capturing both direct and water reflected views in a single exposure. These two methods can recover camera parameters and waves in addition to the scene structure and appearance, enabling its application to unconstrained, already taken images. Experimental results demonstrate its robustness to waves and its effectiveness when applied to arbitrary images taken in the wild. We believe the method has strong implications in a wide range of domains, not just in computer vision and graphics, but also in photography as a new visual media, as well as in image forensic analysis as visual cues for image tampering. Thank you.